Good evening, everyone. So, today I'm going to explain about my work. My work is on the synthesis and recycling of hard magnetic material, enhancement of the magnetic properties of the magnetic materials by chemical methods. NdFeB and the samarium cobalt magnets are the strongest magnets that humans ever created. So, NdFeB are even stronger than samarium cobalt magnets. So, I have worked on both the NdFeB and samarium cobalt magnets, their synthesis and enhancement of their properties. But in this presentation, I will talk only about the niobium iron boron magnets. There are different ways to enhance the magnetic properties of the magnetic material, but I mainly worked on the crystal structure of the magnetic material. I did some substitution in the NdFeB and samarium cobalt magnet and enhance their magnetic properties. And secondly, I also did some work on the recycling of the NdFeB magnet by the chemical method. So here is the experimental process for the substitution reactions. So reaction starts with the chlorides of the Re and Fe. Re is the rare earth elements, and in my experiments they can be different lanthanides like the Nd, Dy, Tb, Gd, Pr, Eu, or some other rare earth elements. I tried quite few. And in the first step, the different rare earth chlorides, they are converted to the rare earth hydroxide and iron hydroxide by the co-precipitation process. Sodium hydroxide 3 molar was used for as a co-precipitating agent, and the hydroxide obtained by this process were converted to the oxides, and this was done by annealing the hydroxides at 900 degrees Celsius for 30 minutes. And then mixture of oxides obtained, it was mixed with the boric acid and calcium hydride, and reduction diffusion reaction was carried out in the tube furnace. This reduction diffusion reaction happened at the 1000 degrees Celsius, and it took almost 3 hours in the argon atmosphere. And by this process, the ReFe boron magnetic particles were obtained, and some calcium oxide was also mixed with these particles, and this extra calcium oxide was removed by washing with the water. For the substitution reaction, I used the Dy, Tb, Gd, Pr, Eu, Ho, and Er, and I substituted them for the Nd in the NdFeB crystals. And I also substituted the iron with manganese, cobalt, and copper. The best results I got, they are with the Dy, Tb, Pr, and the Gd. So here I will discuss mainly about these 4 substituents. So here are the 4 different compositions in the table, and when I substituted the Dy, Tb, Gd in the Pr, and the 4 different composition, like for example, first we see with the Dy. So in the Nd, Re mean Dy, and the Fe and the boron. So I used 4 compositions: the Nd17, Dy 1, Nd16, Dy 2, Nd15, Dy 3, and Nd14, Dy 4. And similarly for the Tb, Gd, and the Pr. Iron and boron, their ratio was kept constant, and the magnetic properties like the coercivity, remanence, and the BH max are given in the table. And in the bottom, there's only NdFeB without any substitution. So here, after the comparison, we can see like the Dy and Tb, they gave the best results and enhanced the magnetic properties up to the maximum. So here are the XRD and SEM results for a substituted and unsubstituted NdFeB magnetic particles. First I will talk about the XRD results. So when here are the 4 results: the NdPrFeB, NdDyFeB, NdTbFeB, and the only NdFeB. So in case of the PR substitution, the peak shift in the XRE, it's actually there's no much peak shift, but in case of the Dy and Tb substitution, the peak shift is very prominent, and this is the reason that the Dy and Tb, they have the smaller atomic radius as compared to the Nd because of the lengthened contraction. So after the substitution with the dy, the crystal size becomes smaller, and because of the overall reduction in the crystal size, the peak is shifted to the right side and the theta value is increased on the XRD graph. So beside this, all the XRD results, we can see the peaks are almost same. A few ND peaks are also we can see here, and they increase the coercivity, the extra ND peaks. And as long as the SEM results are concerned, the overall particle size after the substitution, it's decreased. And in case of the unsubstituted NDFEB, they have the maximum particle size, and in case of the substituted NDFEB particles, the dy substituted particles, they have the minimum particle size. Reason behind the enhancement of the magnetic properties is the ferro and antiferromagnetic coupling between the rare earth elements. So when there is only Nd in the NdFeB crystal lattice, the Nd and the iron both are ferromagnetic coupled to each other. But when we substitute with some heavy rare earth like the dy and Tb, so they couple to the Nd and iron antiferromagnetically, and because of this antiferromagnetic coupling, the anisotropy energy of the crystal is increased. So overall magnetic properties, they increase. And the boron in the crystal lattice, it's non-magnetic, so it doesn't play any role in case of the enhancement or reduction of the magnetic properties during the substitution reactions. Recycling of the NdFeB magnet sludge was also part of my research. So I recycled the NdReFe boron magnet sludge and produced the NdReFe boron magnetic particles from the chemical processing of the sludge, and then we enhance the magnetic properties, especially the BH-max, by ball milling in the ethanol. This is the simplest process for the recycling of the NdFeB until today. Here is the experimental process for the recycling of the ReNdFe boron magnet sludge. And the first step, it was the obtaining the sludge. This sludge is produced during the cutting of the NdFe boron magnets, and the sludge obtained was leached by the sulfuric acid, and leachate is actually the sulfate. The sulfates of the Re and the Fe. Re are the rare earth elements, and the Re in this leachate are the mixture of the different rare earth element actually. So by the ICP analysis, we find that this is the mixture of the Nd, dy, Tb, and Gd. Actually, all the commercial NdFe magnets, they use the different kind of the rare earth elements. In the Gd, they increase the Curie temperature, and the Tb and dy, they increase the anisotropy energy and the BH-max and MR value. So this leachate of the Re and Fe was annealed in the air at 1000 degrees Celsius for 30 minutes, and mixture of the rare earth and the iron oxide was obtained. And this mixture, it was added with the boric acid and the calcium hydride, and the quantity or the ratio of the rare earth was quite low as compared to the iron. And in order to produce the NdReFeB magnetic particles, we needed to add some extra Nd oxide, so that additional Nd oxide was added to this mixture, and this mixture was pelletized, and reduction diffusion reaction was carried out at 1000 degrees Celsius for 3 hours in the argon. And in this way we produce the ReNdFe boron magnetic particles. So they also had some calcium oxide, the non-magnetic phase, inside it. So how this calcium oxide was removed, we will talk about it at the end of our presentation. Before presenting this slide, one thing is very important to be cleared, that the sludge, it contained the Re, Nd, Fe and the boron, but the Re concentration as compared to Fe concentration was quite low. Usually in the sludge or like in the magnet the Nd is more than 2 at 2.3 or 2.4 like in the commercial magnet and Fe14 and boron, but in the sludge there was not enough rare earth, so we knew it by the ICP analysis. So before the reduction diffusion step during the synthesis process we added some extra Nd. So because of the addition of the extra Nd, we were able to compensate the low Nd or Re amount in the sludge. And then we added also some extra Nd and got 7 different compositions. So NdRe 1.6 Fe14 boron is the original composition of the magnetic particles. Those were recycled from the sludge, but because of addition of the rare earth, different compositions were obtained. Iron and boron, that's always constant, we didn't add any iron there. So iron is 14, but because of adding extra Nd, the NdRe quantity was changed, like 1.7 and the NdRe2 or NdRe 2.3 or NdRe 2.6 or NdRe 2.9 or NdRe 3.2, but iron is always 14 and boron is always 1, so that ratio is constant. And here we got the 7 XRD graphs, and similarly we got the 7 different MPMS like the data. And we didn't show here the magnetic hysteresis loop, but in the paper that's available. So we extracted some results from the magnetic hysteresis loop for the squareness ratio and the MS and MR and coercivity. So we can find from the MPMS data that as long as the MR value is concerned, the NdRe2, that's the best composition. And if we talk about the coercivity, then of course the Nd Re 2.3 or 2.6, that's the best one for overall magnetic properties. So like the Nd and the Re2, that's the good composition. And if we talk about the XRD, so for if there is no enough Nd or Re, like in case of the NdRe 1.6 or NdRe 1.7, the good phase was not obtained and there is a lot of impurities in the product. But when we added much more extra Nd, so we also got some extra Nd. So from this composition we were able to optimize some good product with the ideal magnetic properties and ideal structure. This slide shows the mechanism of the reduction diffusion process. At 32 degrees Celsius there are all the reactants, all the oxides, boric acid and calcium hydride. So at first step, at 170 degrees Celsius, the boric acid is changed to the B2O3, and at 300 the oxides of the boron and iron are reduced. At 620 some rare earth oxides, they are reduced, and ReFe oxides, they are also reduced. And at 820 degrees Celsius the overall diffusion process is performed. So the base of this data is the TJ data that's available in the supporting information of our paper. Calcium oxide produced during the reduction diffusion process is not good for the magnetic properties of the final product. So 2 different methods were used to remove the calcium oxide. One was the washing of the product with the water, and the second is the washing of the product by the ethanol ball milling process. So in the ethanol ball milling process, the particles there were separated more efficiently because of the ball milling, and the crystallite of the product that was also improved because of the vigorous ball milling. So overall calcium quantity was also reduced in the final product shown in our paper in the supporting information. So the BH max of the ethanol ball milled product was almost doubled as compared to the water wash product, and there were the 2 reasons for that: the removal of the calcium hydroxide, and the second was the improvement of the crystalline structure. And the detail of both the mechanisms are shown in our paper. Thank you everyone for listening the presentation. Special thanks to the professors of the chemistry department for selecting my work and honoring me for selecting as the best graduate school researcher for 2020. Thanks to Professor Kang for his guidance and support and help in writing the manuscripts. And thank you for the Dr. Kim Dong-soo. in his help in the experiment and characterization, and also thanks to Professor Lee. Thank you, everyone.